This is a really cool slide.
So we're live on YouTube, Chip.
Nice. Cool. Thanks, Omar. Hi, everyone. Today we have a very exciting talk about Robinhood Markets Future Store by three really amazing engineers at Robinhood. So for introductions, Rand is a staff machine learning engineer at Robinhood, where he leads the machine learning platform, especially focusing on model serving future store and generative AI infrastructure. Maybe if you have time, we would love to ask you about the generative AI infrastructure. He loves solving machine learning challenges and is a Kaggle competition master. Maybe we can also ask you about like tips for like winning Kaggle competitions. So Tushar is a senior machine learning engineer where he works on developing the infrastructure for machine learning use cases. When he's not working on feature store and notebook infrastructure, he loves to learn more on everything new in fintech and AI. So Vidya is also a senior software engineer at Robinhood, where he works on developing and maintaining the machine learning platform. He likes to spend his time tinkering with robotics and home automation projects. So you guys all have like really cool hobbies. In the benefit of time, let's start with the presentations. I would really love to ask all of you about what is new in fintech and AI, and also home automation project, or maybe you can even see some of the images. Cool. Let's get started.
Right, sounds great. Thanks a lot for joining. And we will post regularly. So if you have any question, feel free to post it in the chat. When we get time, we will we will answer them along the presentations. All right. So today, Tushar, Vidya, and I are here to present you how we build up the Robinhood Markets Feature Store. There's a 4 stage. We are going to talk about that. We will go through them one by one. All right, here's today's agenda. We will talk about the history of the system, how we build up from nothing to adopt Feast, to rewrite them, and finally to some new progress in the field. We will focus a lot more on the aggregation feature part. I know many company or commercial product have solved this aggregation feature problem. We take a slightly different technical choice. So we will share what are those and why we make those choice. And we will talk about our user-defined aggregation feature. I think we just co-complete on these functionalities. So we will talk about why we need to do it. All right. And also we talk about our future work. All right. So first, let's. I am assuming most folks here knows what is a feature store. I'm just going to recap. Thanks Tecton for creating this nice figure. So a feature store is an infrastructure to consume data from batch source or streaming source. It comes into the system, run some transformation. So you see there's some compute component in the infra. Then it stores the feature value. So you have a storage layer to store the feature value, either some intermediate result or the final values. And you have a serving layer to provide this feature to machine learning models for making predictions. There's also component like a registry to allow our end user, data scientists, to define their features to find what features are available. They will also be using the infrastructure to generate features for model training. Certainly, you also need monitoring on the system because if some feature pipeline is broken, you want to know it as soon as possible and fix it. So this is an infrastructure built in Robinhood to solve this problem. So we have all the components mentioned above. All the things are built internally. And the reason why it's called Beast, it is because it's built from Feast. So now it becomes a Beast. And originally, actually, we thought about onboarding some vendor services. There was some restriction at the time, back in 2021. So we didn't get a chance to use some vendor solution. And there's also some lesson that we can also share later. So in Beast, there's a few support feature types. For example, batch computing feature. A typical example is you want to calculate how long a user stay with Robinhood. So you don't need this feature to be updated in real time. So basically, what you need is just a offline job to compute this feature value. Basically, just to count, okay, when this user joins and up to today, then you ingest the feature to a fast storage and provide those values to the machine learning model. We also have aggregation features. So the typical example would be how much debit card transaction a user has made in past X day. The X day can be 1 day or maybe 1 hour up to 180 days. So those are what we call the aggregation features. We will also have derived features. Basically, you may use those batch computing feature or aggregation feature as parent features. Then you derive out of it. Here is example on, okay, can I, if I store some timestamp features as integer, can I convert it from equal to time string for so that I can use it in a slightly different format. And keep in mind that this feature is not just used for machine learning models. Some of them are used in rules. Some of them are used for other purpose. But what we see feature is a way to describe a user's behavior. And finally, we have the user-defined aggregation features. So basically, we support any weird computation. There are a few of them in the Robinhood. All right, next. So I'm going to talk about the very V0 stage of the feature store. Basically, there's nothing at all. So their scientists have to implement their feature transformation pipeline. Then they will store that features in a Hive table. Then they pass it to product team. Product team will have a job to load the Hive table into Redis. When they want to make a prediction or model prediction, they would read out the features in their Redis and send it to the model server. So at that time, we do have a model serving service. That's the first service we build as a machine learning platform. And their scientists would be also in charge of all the model training, the feature generation. As you might imagine, there's a lot of pain point. Every new feature have to, you need a product team's engineer to onboard. And there's a lot of manual work over there. There's no feature discovery, no monitoring, no lineage checking. And also the time, the storage format is not very optimized for the feature use cases. So we saw this pain point, and that's why we start to build a feature store. So at the beginning, we didn't build our own feature store. We tried to buy some vendor services. We do some evaluation. Eventually, I think there's the main reason we didn't continue is most of them are not compatible with our internal infra. So we basically get a hard no from our platform team. So that's why we start building it ourselves. And that comes to the stage one. We didn't build everything from scratch right away. We actually start with Feast. So on the left-hand side is the Feast architecture at that time. I remember it's 0.94. That was the architecture. We actually, for the first version, we take out only a few components in the Feast. So basically, the Feast call is the feature registry to allow you manage your feature definitions, like what's the name of your feature, what's the type, what's the description. There was also a Feast serving component. Basically, what it does is it reads data from Redis and provide an API, a standard API for you to read feature values. So we take out those two components. We deploy them into one single pod in Kubernetes. So basically, we have, if you see the right-hand side, we have that Feast call process running and the Feast serving process. They are all running in a single pod. At that time, I remember the feast call and feast serving only expose gRPC endpoints, and we don't have a gRPC support that well at the time within Robinhood. So we have a very simple server written in Golang to convert that gRPC call into a REST API. So that was the stage one. We take out some feast component, we put it into our internal infra. We try to avoid forking feast because we just want to ship the product quickly and see how many whether it makes sense for the data scientists. We do rewrite the whole feast Python SDK. There's a lot of redundant Python dependencies that we don't need. So we want to make the SDK really, really slim. We also rewrite the whole ingestion job because we don't have a good Java support at the time. So we actually use PySpark to implement all the ingestion. And we don't have any streaming feature support. So that comes to the now it's a better diagram and a better system architecture. So data scientists will still need to write their own feature transformation pipeline. They run a Spark job to generate a Hive table. Then the rest are taken care of by our team. We manage ingestion. So we have a Spark job to ingest the data from Hive to Redis. We allow them to register their feature to a metadata store. And we build a UI so people can see what features are out there, what's the type. And we also calculate the statistic of all the features so people can see between each state how the statistics are changed. We adopt something called like multi-single tenant architecture. So each team can have their own Redis cluster. This is for resource isolation. Or if some team, they have much more traffic than the others, we actually use it as a way to provide different kind of resources. In terms of responsibility, product team would be responsible for managing the upstream table. So up to the Hive table, it would be managed by a product team or data scientists. So we would be responsible for all the rest, from ingestion to serving, and also the model part. So I will pause a bit to see if any particular question we have.
Ran, there are a few questions on the chat on which tenants we consider to onboard before deciding on building our own, and like why did we move in that direction? Right.
So we can talk about some option we evaluated. So things may change in 2023. At the time we evaluate Hop's work, we feel the platform is good, but it's overly complicated because we only want to take out the feature store component. And we also evaluate Tecton. Actually, we pushed pretty far when onboarding Tecton, but at that time, they don't support in-house Spark cluster, and that was quite important to us. So that's why we didn't continue the Tecton onboarding. And then we also consider the AWS feature store, and at the time they don't have much functionality. So yeah, and that's a few commercial options we evaluated, and then suddenly we evaluate fully rewrite it. We feel that's too much work, too risky. So Feast was a good option because it can speed up the development. We can see how good it is before moving forward. Yeah. So we can take one more and then we can continue. Is anyone, Tushar, do you mind picking one?
Yeah, so people can ask the questions, choose a slider. We also have about 10 questions on Slido so far. I think just one quick question about the UDF, since a lot of people upvoted it. What are some examples of UDF and how is it different? What's the difference between a normal functions and a UDF?
Right, that's a fantastic question. Tushar will talk about that later. He will give you an example on the UDF. So I guess it's a good sign for us to maybe continue. Okay, so next, here we come to stage 2. So in the end of 2021, so we shipped the product. We built it from Feast. I think we onboard more than 500 features in a few months. So this speed you cannot it cannot be achieved with the V0 version. Like if you don't have feature store, you don't have such velocity of onboarding features, even it's a simple batch computing features. Now, then we go to 2022, the early 2022. So we also identify some problem with the Java process in Feast. So that's one, we didn't fork the Feast repo because we hope to see like more improvement to the Java code, and then we don't need to maintain it ourselves. But we found out one, it makes us very, very hard to debug anything that happens in the Java process. And also JVM starts quite slow. So we have a quite long kind of start time when bringing up those two processes. And also at that time, there was a big push from the Feast community to rewrite all their services in Python. So the Java version was not well maintained. So we don't see it will be well maintained at the time. Then what we did is we look into, okay, what are the functionality we have seen, we have used from Feast. It turns out we don't, so the RPC method that we use are not a lot. So at that time we decided, okay, let's just fully rewrite that in Golang just to merge this process into one Golang server. We spent 1.5 months. It's not too bad. So we first rewrite the Feast serving process. So that's much simpler because it only reads the data from Redis and convert it to another format to return. So we first I think we spent 2 weeks to rewrite the Feast serving, and then another month to rewrite the whole Feast call to only implement the RPC method we need. So that comes to the right-hand side, that part. So it still exposes a REST API. Once a user asks, okay, I want feature ABC. So if it comes to something called feature retrieval, it would kind of, based on their feature name, we identify, okay, should we read this feature from Redis or should it read from DynamoDB? And all those metadata are stored in a in-memory metadata cache. So it would just, this in-memory cache would just continuously read from Postgres for any updates and cache them in memory. And then if we know like which storage that feature comes from, we will just read them from different storage. We also added, we added multi-storage support to Beast because some feature, like if you don't have a lot of traffic, but you still need to store a large amount of them, DynamoDB is actually a good choice to balance the latency and cost. For in-memory cache, you have to persist all the values in memory, and sometimes you need a much larger Redis cluster. With this Golang server, we were able to handle 17K requests per second with a 4 CPU core pod. I think it's around 20 features when we measure the statistics. All right. Okay, next, we'll dive deeper into the Beast aggregation system. So we sort of mentioned what is aggregation features. So here is the example we will use along the way is, let's count how many MFA changes a user has made in the past 3 days. So MFA is the multi-factor authentication. We asked ChatGPT to write a SQL query. Very easy, right? Sounds very simple. But the user says, I have just a few more requirements to do. First, I want it to be super, super low latency. The same, you have to make sure if I read hundreds or thousands features, I want the P19 still less than 100 milliseconds. And I want to support point-in-time join. So I don't need to have a very complicated SQL query to generate training features. And I want a super high freshness, like if I make some change on my app, this value should be updated in a few seconds. And I want it to be super easy to use. And I want it to support like a lot of aggregation type, min, max, distinct count, there's some other weird type. And it turns out it is one of the most challenging problems in Feature Store to build these aggregation features. And next, I'm going to talk about how we solve it. So I'm not sure like if other feature stores also adopt this concept, but we propose something called the event first architecture for feature engineering. So basically, we treat events as the first class citizen. So both online and offline. So basically, you can see any NFA change record as an event. So it will always come from a Kafka topic where we would do some processing using Flink to pre-aggregate the user's event. We store this pre-aggregation result to some storage. And in the serving time, we will aggregate them on the fly. So this part is not new. This part, at the time, we already saw the Tecton's blog. A lot of ideas come from there. But what we push it to the limit is this event idea. So we always assume you can log all those events in the Kafka to a Hive table. And then in the offline, we will reconstructing all the feature values only using those event data. And each is a Spark job. Spinner is the internal code name. So we have a Spark job to recalculate those pre-aggregation values for backfill. Yeah, because when you define a new feature, sometimes you might need to wait for, if it's aggregating 7 days or 14 days, you need to wait for a long time for the data to be available in Flink. So what we do is we allow reconstructing that pre-aggregation value, and we backfill that into the storage. And the same job, the same Spark job can be reused to generate training features with point-in-time credits.
So Rex, just a quick
yeah.
question. So you said that like you had to wait a long time for the feature to be available in Flink. How long is long?
Wait, that's a good question. So it depends on how long your aggregation window is. So if, let's say, imagine you don't have the bottom part, you only have the Kafka and the Flink part. Our Kafka retention policy is 2 weeks. And if you define a feature like aggregating over 7 days, actually it means we need to wait 7 days to get the, so after your feature deploy, you still need to wait for 7 days for the event comes in to get a correct value. And also if you aggregate a longer time window, you basically don't have that data in the Kafka.
I see. So the event first architecture means that you log on the event so that you can backfill and don't have to wait 7 days.
Exactly. So we basically treat event as first class citizen in both offline and online. So it's only possible if you can log basically all of them into a data lake for later processing. Yeah. So that's the concept we figure out. It may not be suitable for every organization, but for us, we find very convenient as a way to unifying the offline online computation. And that's okay. This might be a clear viewpoint of how the event flows into the system. Okay, so let's look starting from the left. A user just changing the NFA, so that activity is published to a Kafka. Okay, inside the Kafka, you only have the raw events. The raw events will go into a Flink layer. The Flink would do any filtering transformation. It also do the pre-aggregation. And after you have the pre-aggregation, it writes into another Kafka queue, and we have a Kafka consumer called feature updater. It will keep updating those pre-aggregation results into the storage. And here we use DynamoDB as example, but you can use it also implement with Redis. So this is the real-time portion. What we mentioned just now is, okay, there's also a Spark portion. So this Kafka event would be locked. It depends on your retention policy. You can maybe going back to 1 year of event. So it go into a Spark. It generates again the aggregated feature, but at different different time, different day. We have this backfill table. Then we load this historical aggregation into the DynamoDB again. Then in the runtime, when you read the features, depending on how many days you want to aggregate, it will be able to combine those aggregation on the fly. And in the training time, the same job, but we just tweak the time window a little bit different, so you can generate point in time correct training data, and you can build a model on top of it. And you see there's a concept called feature SQL, and next I'm going to talk about this how the configuration looks like. Right, so we actually have a SQL dialect, what we call, we build that internally. On the left, you can see that's how a data scientist would define the feature, an NFA change feature just now. So we have a Kafka source. We will select some field from the Kafka source, and we do some filtering, transformation, and we will specify what's the feature name or the prefix, which column you want to aggregate that on, what's the type, aggregate function. Okay, this is a very standard. We learned this interface from Tecton again. And then we also have a concept called feature table. Basically, it's a logical grouping of the features. We write a SQL parser to parse what happened inside here, the Kafka source. By parsing them, we are able to transpile them to a Flink query, like the one on the right, and a Spark query. The Spark query will look much more different, much more complicated. It should always be code generated. It's not very easy for human to write this. Maybe ChatGPT can do it nicely, but we transpile that to a Spark query. So this YAML would be used in the production job in the Flink, and it will also be used in the Spark. So again, this is another view of the what I just talked about. We have a SQL parser. We have some really not the full SQL IR, just some but some intermediate representation of the parse result. Then we pass into some converter to generate the Flink query and the Spark query. We also support UDF, so you can define UDF, and the UDF can be used in the SQL. It's really a reduced set of SQL grammar. We don't support join, we don't support group by, so it's only a very small set of the SQL grammar for the feature engineering. Yeah, we use PyParsing to implement the parser. We find it's a pretty neat tool. If you are a Python fans, this is must have tool for stream manipulation. Yes, we already talked about we co-generate the query, and the YAML will be used in the deployment, in the debugging. Okay, next I will hand over to Vidya to talk about the Flink portion.
Mm-hmm. Thanks, Rand. So I'll talk about Flink. So Flink is like the core component of like the streaming aggregations, the stream part of the aggregation system. So Flink is an open source unified stream and batch processing framework. It can do like distributed stateful computation server onboarded streams. The way it does is it divides onboarded streams into like a logical concept called windows. So in that way, like it can do stateful computations over like the windows and unbounded streams. It offers like low latency and high throughput. We observe like sub-second latency and like hundreds of thousands requests per second latency throughput. And it can work with both real-time data sources such as Kafka and like historical data sources such as Hive. It has built-in support for exactly once processing, and so also has fault tolerance with external checkpointing. It can process events based on like event time or processing time. Event time is very crucial in distributed systems because there would be like a huge skew in that time when like the events were actually generated versus when they were actually processed. So we operate like in our system, we operate on like Flink on the event time. Next slide, please. Okay, so this is like the internal architecture of like how inside the how the processing works inside Flink. Okay, so first we read from a Kafka source. Okay, there we support like reading from like multiple different Kafka sources. Each Kafka source can have like a different message format. So we have like a protocol definition for each Kafka source. We like unmarshal the message into the using the protocol. Okay, then there's like a layer that dedupes the messages. So sometimes like the event, there can be like duplicate events inside our source topic. So we have like some like temporary cache that deduplicates messages. Like if the same event ID occurred in like the last 6 hours, we cache that and remove that from. And then like using the schema from the protocol message, we construct a streaming SQL table. Okay. So on top of the streaming SQL table, there's a continuous streaming SQL query that is applied. So like the in the example that like Rand showed earlier, right, the Flink query that is generated is applied here. So that query takes care of two things. One is like transformation and filtering events. So like this particular source may have like events like a wide variety of events, but here you can like kind of narrow down like the specific events that you're interested in and like do some kind of data transformation. So we support like nested protobuffs, parsing nested protobuff schemas, as well as like JSON fields too. Like certain fields inside the event can be JSON, so we also support like JSON parsing here. Once like the streaming SQL query is applied on this table, it generates like a another like dynamic stream. Like from there, we have like a key by operator. So the key by operator, it extracts the entity IDs from the message and like kind of divides them into each key stream. So each key stream has like only events of a particular entity ID. So an entity ID can be like an user ID. So basically, all of the events made up by a particular user can go into a separate stream.
Can you like speak a little bit slower? Yeah, thank you.
Sorry.
Yeah.
Okay. So the key by operator would divide them into particular key streams. On top of the key streams, we have like an window operator. So based on the type, based on the window size of the particular aggregation that we are planning to perform on this particular stream, the window operator would be like either be like 15, like the size of the window operator can be like 15 minutes or like 1 day granularity. So whatever is the granularity, like the window operator would kind of assign the event into like one or more windows. And from there, we have like an aggregation operator that is like one aggregation operator per window. So it can be like the aggregations that we support in Flink are like kind of like very standard aggregations, like sum, average, count, minimum, maximum, like latest, and so on. So then like the aggregation operator, like the output from the aggregation operator is again like converted into like a different protocol schema than that we again write to like a different Kafka topic, that's output Kafka topic. There's another system that reads from the Kafka topic and writes to like the beast aggregation system, but I'll talk about that later. Next slide, please. Yeah. Okay, so this is like how like the window looks like in vendor semantics look like in Flink. So basically, for each user, there can be like multiple windows. Like let's say each window is of size 1 hour. So like for user one, like events that fall in that particular time window are like just assigned to that window, and we do the aggregation logic on top of that particular window and just do that. Flink also supports late events. So basically events can like come in out of order. In those cases, we have like a buffer time, like let's say 15 minutes. So like even after like 15 minutes after the end of the window one, even if the window like event occurs late, the window is still retained and the event is added to that previous window and then like calculated and published to like this data cluster system. So we support like based on the window length. Sometimes like some features have like a 7-day window size. For those we have like a granularity of 1 day, but certain features are like just 1 day long. So for those we have like a smaller granularity, like 15-minute granularity or 1 hour granularity. So we have like yeah. So based on the window size, we pick the granularity that we support. There's also certain features where like prescience is very important for us. For those we have like implemented a rolling window internally, like a rolling window implementation. In the rolling window implementation, all of the events that fall into a window are stored in memory. So this won't work with for any cases where there are like a lot of events. Only for features like that are like kind of smarts, but and have a very high granularity requirements. For those we use rolling windows implementation. So yeah, we just keep everything in memory, and like clean specifically after like every after expiration we kind of clean up and recompute and publish the recomputed values. Okay. Yeah, next slide, please.
Oh, Vidya,
So,
there's still some people's asking you to slow down a little bit.
sorry.
Sorry. Yeah.
Okay. I could go here. So this is like the beast aggregation system. So this is the next part of the system after like the Flink part. Okay, Flink does the pre-aggregation. Then we call the that's like a beast server that does take care of that takes care of both sorry, retrieval as well as storage. Okay, so we get like a pre-aggregated input from Flink. From there, like the update and endpoint update API is called. Then like the pre-aggregated is again like converted into our update item input format. So then like this would again store them into the database. So currently we support like DynamoDB and Redis. For the aggregation system, we currently are just using DynamoDB. From there, during the retrieval part, like the beast server like fetches the pre-aggregates from the database, then kind of recomputes, like aggregates the pre-aggregates together to compute the final feature. Now in the next slide, we'll like take a deeper look into how it is being done. Okay. So like, let's say this is the pre-aggregate. So like we are calculating the sum of a particular feature per day. So let's say this is like a daily aggregate, like this is a feature with a granularity of daily. So for each day we have like some value, like the day 24 we have like 1, day 25 we have 1, and like for 26 we have like 2, so on. So this is how it is stored inside the DynamoDB. So basically we have a key. The key would be the table name, like the feature name, as well as like the year and month. Like all of the days are like present as like individual columns inside the data store. Okay, so we have like the individual sums for each of this particular day. And then can you go to the next slide? Yeah, so during retrieval part, let's say we get like a retrieve request for like a sum of 7 days. Okay, in that case we would we would fetch all of the 7-day values and do again like a pre-computation on top of all of this. Like we would add the values of each, we would add of each of this pre-aggregated values to get the final feature sum. So this is how the feature retrieval works. And yeah, next slide, please. Yeah, Tushar would go over like the UDFs. Thank you.
Yeah, so hey everyone, I'm Tushar, and I'm going to be talking about UDFs. So as Ran and Vidya talked to you about batch and aggregation features, but what we realize is that even after supporting batch and aggregation features, there were still some features, what we call them as small tail features. They're like a small group of features that didn't fit these standardizations of feature types. So think of these features as some features that could require some complicated join between different event types, or they require some sort of custom filtering logic, or even access to like some Redis database or some state. And to support these small tail features, we created what we call as user-defined aggregation features, or UDFs. So in the chat as well, we have some questions around the example. So let me talk about an example. Next slide. Oh, these two. Bad. Yeah, this one. So in this example, so let's say we are computing a feature that is the sum of deposits for a user in last 3 days. So this is very similar to one of the features we have in-house in Robinhood. So to give you some context, when someone performs a deposit, it goes into an initiated state, which means the deposit has been initiated, but it can also be later reversed due to a variety of reasons and with the financial system. And what we would like to compute here is like total initiated deposits, but exclude the ones that have been reversed for that particular user. So as you can see in this example, a deposit is represented by a deposit ID, the state, which can either be initiated or reversed, and the total, the amount of the deposit. And let's say for the first 3 days, we receive one deposit on each day, and the total sum amounts to $60, and there were no reversals. So the calculation for this feature is pretty straightforward. It's total $60, and we are good. But let's say on day 4, we receive a deposit for $50, but there was a reversal of deposit ID2 for $20. And probably one way to handle this could be that we could remove the reversal values from our total aggregation value from day 2, day 3, day 4, which was $100. So which would give us an updated value of $80. But as you might have guessed, the logic is pretty flawed. Let's say on day 5, we receive another reversal for deposit 1. But in this case, we don't really need to subtract that value from our total aggregate value because we weren't counting it in the first place itself. So this really happens to give you just a recap because in an aggregation system design, once the pre-aggregates are computed, we are no longer, we have the event context. And it wasn't really designed to handle these use cases. And therefore, we kind of proceeded to have UDAFs. Next slide. And before we go into design details, let's talk a little bit about the characteristics of the UDF system and Robinhood. And first, the why. So as we discussed, UDFs really help us in supporting all the non-standard features at Robinhood, which in turn allows us to consolidate our maintenance costs by maintaining just a single feature store and a serving system. This really also simplifies what we have seen, the workflow for our users and data scientists, which helps them significantly with their iteration velocity for creating new features or improving the ones that they already have. And as for the how we are doing this, we kind of take our event-first approach even further with UDS. So now we, instead of just storing the pre-aggregates as we were doing before with the aggregation system, we store the raw event data in our DynamoDB storage. And the custom aggregate functions are provided by the users or the data scientists in form of Golang functions, which are linked to the feature definition, as you can see on the screen. In the feature config. So you see that now when we define a feature, it's UDF name, type, window, and we have a UDF param, which is the Golang function defined by the user or the data scientist there. And these custom aggregate functions are actually used for computing the aggregation at the time of the serving. And we'll see in the next slide how. Next slide, Ryan. So we previously saw this diagram for B's aggregation system, and we talked about like how Flink would pre-aggregate the events to be stored in DynamoDB, which are then aggregated fully during the time of serving. For UDFs, we didn't really have to reinvent the wheel. We primarily use the same architecture, but we just made a few small tweaks. Next slide. Yeah, so now instead of pre-aggregating events during the time of ingestion, Flink only filters the raw events, and we directly store these filter events into our DynamoDB storage. At the time of the serving, Bees fetches these events from the storage and also the custom aggregation logic that was written by the data scientist to compute these aggregations on the fly before returning the final feature values to the client. So that's all. Next slide. I think that's all from us today. And for the next steps, we'll be focusing on solving the online-offline consistency problem for UDFs, also optimizing our offline feature computation speed, and finally, last but not the least, continue to improve our system's observability and developer experience. Next slide. So just wanted to thank you all for attending, and yeah, we'd be happy to take any more questions from the audience now. I don't know how this works, probably Slido.
Hey, this is awesome. Thank you so much. We have a lot of questions actually. So I just did a poll. It seems like most people are already have a future store or building a future store. So, of course, as the audience of this talk, probably like geared towards people who are interested in future store. So, I think we have a ton of questions on Slido. Just a quick note to the audience here, and feel free to post a question and upvote the question they want to answer here. So, the questions that you mentioned about, so the top voter question right now is about EDF, and you mentioned that you already responded to that in the talk. And I got a quick question follow up, like how what is challenging about solving the online offline consistency for UADF?
Yeah, I can take that one. So if you really think about this, we open the gates for doing literally everything and anything with UDFs. There is no like we tried our best, but there is no really concept of abstraction or standardization here. So if someone wants, they can actually even call like a third party, not third party, but like some other teams, Redis cluster, get some information, use that in constructing their features on the go. So this makes it really challenging because when we have to write that training job for getting the training data, we need to replicate probably that logic somehow and do that at the time of training. And also the server is written in Golang. Our stack that we have for creating either like any batch computed data is nowhere uses Golang. So that makes it even more complicated there. Yeah,
Okay.
anything to add with your brand?
No, this is very helpful. So the next question is, who is responsible for managing the metadata store, ensuring features are properly documented and can potentially be shared between projects?
That's a great question. We do have some CI system to capture. So when you deploy some new features, there shouldn't be any duplications in the feature name, for example. We do a lot of we have a lot of tooling built to really make sure that the feature that this definition of metadata is correct before rolling out. We are trying to enforce everyone to write descriptions, but this is not easy job because they might just say, okay, import something or the description just reflecting the feature names. So we are still need a better way to help people write descriptions. Yeah.
I see. So the next questions could be, if you were to build this again, what could you do differently?
Yeah, that's a great question. So I would say building up the aggregation feature part takes a lot of end resource. It takes us 4 engineers 6 months to build up the whole thing. If you want something quick, so just use a vendor solution. It's 2023. I think we have a quite mature feature store offering out there. But the UDF, I don't see any others are solving the problem. So if you cross that bridge, you already build your aggregation features, maybe you can move faster with an internal team, because building up internal product, you don't need to worry about a lot of things like security or like setting up AWS sub account. As a commercial offering, you have more problem to solve. But if you already cross the aggregation feature that stage, I think building up internally would be faster.
Yeah, yeah, totally. I think we're really asking for a question on this as well. So I do. The next question is, can you dedicate more? Can you dedicate more on spinner job and how it backfill past data? Is there any skill in online, offline? Who asked these questions? I'm not able to. So did you get the questions?
I think I saw sort of understand that one on the backfill. I think the backfill part, right?
Yeah.
Yeah. So basically, in the backfill, so it's based on the so user have to write those like the big SQL, right? The reduced SQL grammar. You can translate the same logic into a Spark query. And the main difference is just the data source. So you do a sort of a group by each user, and then you query out the time range that you are interested in for that particular user. Then you can run the same SQL logic on top of that event data. So remember, we always log the events into a data lake, and the events is usually has a primary key related to user, bank account, wherever. So in that Spark job, you just do a group by the entity you are interested in. Then you see you will have a time series of event. Then you do again, you just filter out the event you don't need, then apply the compute logic. Yeah. So that's roughly how we handle the backfill or the training data.
I see. So it seems like the feature definitions are in SQL, and then you run that on both Flink and Spark, Flink for online and Spark for offline. But I imagine that Flink SQL and Spark SQL could be different, right? Then how do you ensure, do you run into any problems with inconsistency?
Yeah, so we found the Flink SQL and Spark are pretty similar. So every function we need, you always have something very similar name. I'm not sure if because they all of them use calcite as a SQL layer, but we find out most of the time you can translate that pretty easily. Yeah.
I see. So even like time semantics, watermarking is covered in Spark streaming as well. And sorry, in Spark SQL.
Okay. So we don't have the watermark semantic or the window in this SQL. So that SQL is only for transforming your event, filtering your event, and then it's really a restrict set of SQL grammar that we support. So because we want to simplify the problem a bit, so there's a lot of SQL functionality we are not providing.
I see. Okay. So I think I guess it's also answer the question about like, can you write features in SQL? I think another question is Spark fast enough for the batch jobs?
So right now, so far so good. We are able to further improve it for sure. We have some idea. Right now it's still written in PySpark. We use a lot of UDF in Spark, so that will slow down things. We certainly want to rewrite that in Java. Yeah, now we have much better Java support.
Okay, so it seems like Java is the language to go. I see.
Yeah.
Because of the Flink ecosystem. Okay, so I think like because you just mentioned Spark UDF, and I saw like there's still questions about the UDAF. So what's the difference between like Spark UDF and the UDAF?
Maybe Tushar, do you want to take this?
Yeah, so we realize that the name can be confusing, but they're pretty different things. So with Spark UDF, you have like a native concept in Spark where you can create custom functions. So this is kind of our attempt to have those custom functionality for features, but it's not related to Spark. Like all of the computation happens at the time of serving when the features are calculated from raw data. So that's the similarity and the difference between both of these. If that helps.
So what makes it of user-defined functions?
So think of it this way. So aggregation functions are pretty well defined. So you have aggregation, the sum, count, those kind of simple aggregations. But then when you start going into more complex aggregations, let's say you have to do a sum, but only for a few particular deposits. Those require like some custom logic, custom rule, which is defined as a Golang function by the user or the data scientist who creates the feature. And that logic is called UDF, user-defined aggregation feature.
Did you say that user had to write in Golang?
Yes.
Oh, so like people had to know like SQL, Java, and Golang.
So this is only if you cannot get done, like a feature cannot be a batch feature or aggregate feature. There was a question on the chat as well. If something can be solved with aggregation features, that is always going to be the preference. We're always going to recommend someone to do that because at the end of the day, it's still very much config driven. UDFs is pretty open-ended, and we only recommend doing that we have like almost 10% of features in Robinhood that kind of are UDFs. So we only recommend doing that like if there is no option with batch features or aggregation features, and then yes, they have to write Golang.
Well, 10% of the features are UDAF.
I think it's
10%
10%
of the
of the real
aggregation.
time. Yeah.
Okay,
The aggregation features, real-time features. Yeah, sorry.
I see. So I guess UDAF is pretty very small, like a fraction of it, like 1% or something. Yeah.
Yeah. Overall, yes.
Yes. Yeah. So if you can solve it with batch computed, we will just say, okay, please solve it batch computed. Don't waste more resource, or it's just more robust to have a Hive table up there and ingest. Then if you really need high freshness, actually there's a bunch of them. They really need high freshness. Then if it's simple aggregation, just use the existing system. So only the one you feel, okay, this feature is so important, and there's no easy way to implement that with the previous two systems. Then that's why we have the UDAF. That will also help us. So we are a small team. We can keep building out abstraction to solve your particular use case, but this long tail is very hard for a small team to cover.
I see. So like, is there like some guideline on like from as a data scientist, right? I feel like given by the number of questions on UDAF, I imagine, not sure, Robinhood data scientists are maybe confused on like when to use simple aggregations, or when to use batch, or when to like take out the UDAF. So do you have some guideline, like what kind of features are suited for UDAF?
Yeah, so batch and aggregation is pretty simple. So if you don't need anything real time, or you don't have a real time use case, you just stick with batch. If you're fine with like, let's say a day's latency for your features, you stick with batch. If you need it to be more real time, we recommend aggregation feature as the choice. And usually, as we said, like mostly 90% of those features can be handled by aggregation feature, like sum, count. These are most of the features that are required. But then if the aggregation feature cannot handle your use case, yes, you go and write UDF. But UDF, we're still onboarding it. At this point, we're onboarding those features, and we usually recommend that if you're writing a UDF, you also come and talk to us regarding what your feature is, and we help you decide like if this can be handled some other way. If there is no other option, then we help the user with the UDF development.
I see. So it's still very white glove support for UDAF.
Exactly,
I see.
yes.
So okay, so for the next questions, is on the design principle. Do you allow deployed model endpoints to access online feature store for real-time features, or does a calling service need to provide those?
I'm trying to answer it that so there's no restriction on what feature you can read from the model server, primarily because we also manage the model serving infra, so we sort of know what feature you're consuming. Yeah, so there's no strict restriction on who can access which. But we do have a concept called project based on the team level. So we do have some kind of security group to who can access a particular resource. Yeah.
I see. Okay, thanks. The next question, I guess you already answered, is like you use what do you use for transpilation? And I assume you said like Calcite, right?
Yeah. So we didn't use Calcite. We just write a SQL parser ourselves, and you have a abstract syntax tree. Then when you can visit those the nodes inside the abstract syntax tree to do the transpilation.
I see. Do you foresee that could be a problem in the future, or do you think that the UK is going to keep on the Flink SQL syntax pretty simple?
Yes, right now we keep it super simple, and I'm not going to deny there's some maintenance cost to on the parser. We are looking into some other open source software. If someone are willing to maintain the parser for us, we will for sure adopt your open source packages. There's some potential. I think there's one called SQL Parse. There's also one to translate between SQL queries. So we are looking into that. Yeah.
Do you know about IBIS?
I heard of it, but I don't know the details.
So yeah, so they do that kind of stuff. Yeah. Let me. Yeah. Let me just share it with you here as well. Cool.
That's great.
So
Then we can have a better solution now.
we're working on a ton of stuff like that because we also have a compilation layer to compile between different computation engines. And we find that like every different dialect is slightly different, and especially if you have a lot of time semantics, it can be quite painful.
Totally.
So, the next question is why Flink instead of Spark streaming?
That's a great question. Actually we talked to other companies. I know Airbnb was using Spark streaming. There's also another feature store product called Quark. I forget the name, but they also use Spark streaming. For us, we don't have much choice. Because option one for us is we maintain our own Spark streaming cluster. We will be the only users. Versus Flink has at least a larger user base inside Robinhood. So it was a no-brainer for us to pick Flink.
I see. So it's just like you already have Spark cluster.
Yeah, so we have a much better Flink support internally compared to Spark streaming. Yeah.
Oh, interesting. So I guess it's more like you use a lot of Flink, you have a lot of support more than so it's not because of like Flink is better than Spark in any way in your experience, but it's just like
it's good for us. Like all the core team members are here. So if all of us only 3 of us maintain a Spark streaming, it can be too much. But if there's some problem with Flink, we can also find other team members, like streaming team members, to help us.
I see. So actually I know that's like we are at time here, so I thought I know that some people who asked the question are still here, so why don't we just like stop recording and we can all have like a more informal chat, and the people who have questions can just jump in. How does that sound?
Sounds great.
Okay, cool. So yeah, Pushka, do you want to ask a question?
Yeah. So